추천 리스트를 보내는데 제가 박기훈 학생 맞죠? 박기훈 학생 맞지? 우리 컴퓨터 학생 중에 박기훈 학생은 제가 잘 몰라가지고 추천 리스트 보내는
그래프 알고리즘 무슨
Thanks for coming.
이런 거 그렇겠죠.
So, yeah. Usually our seminar is on Tuesday, but we didn't want to have a seminar dinner on Christmas Eve. So, so we are having seminar on Monday. So today we have Zixiang from Frankl. He will talk about some polynomial, right?
Okay.
Please.
Thanks for providing me such a great opportunity to give a talk here again. And most of you are the new phases compared to that I gave a talk 2 years ago, and how time flies. So today I will talk about mainly I want to introduce some of the polynomial method and the stability result in such system. This is based on joint work with actually mainly attributed by Dr. Jun Gao and Professor Hong Liu. We finished this work 2 years ago, and I will summarize some tricks and some basics and tricks and further applications of this method. Okay. So let's first recall some problems and results in the field of extremal set theory. So basically, in the field of extremal set theory, the problem asks what can we say about the size or structure of a set system if the any distinct pair of sets satisfy some certain properties. So the operation can be the intersection, the union, the one-side difference, and the symmetric difference. And you can also define any abstract operation you want. And the space can be the 2 to the n, and you can also set some larger alphabet, and you can also set the vector space. And you can also ask some question from the pairwise to the k-wise. So there are lots of such variants, but basically this field usually asks the problem in this form. Okay. So one of the oldest result in this field is Ehrlich-Colorado theorem, which was published in 1960s. So actually, I think lots of the paper also record this story. I also heard it maybe 3 years ago at the commemorate the conference of the Mr. Ke-Zhao's 110th anniversary birth, and his doctor said that they already finished this work roughly 1960s, but due to some well-known reasons that they come back their own country, and when Ehrlich visited Beijing in 1960s, and Mr. Ke-Zhao from flight from the Sichuan University to the Beijing, and they finished this work when they watched some Beijing opera together. Yeah. So this theorem states that for an K-uniform intersecting family, the maximum size of a K-uniform intersecting family is at most n-1 choose k-1. And the upper bound can be attained when the family is a star. The star means every set contains a fixed element. Okay. So and later we will also mention this theorem because the extremal configuration is unique. So so in the EKR theorem, we only require the intersection to be is not empty. But suppose we give more extra assumption on the intersecting on the size of the intersection. For example, the size of the intersection belongs to some certain subset L. Then what can we say about the size? More than 40 years ago, the Frankl and Wilson studied this problem and provided such looks clean upper bound. And later in the maybe 20 years ago, the Snively successfully improved this upper bound from the you can see from the value n to the n-1. Yeah. So and the later upper bound is sharp because you can use some toy from the finite geometry to construct some tight lower bound. Yeah. So another very famous result in this field is Spanner's theorem, which states that suppose for any distinct subset A and B, if the A is not a subset of if for any distinct subset A and B, A is not a subset of B, then the size can be upper bounded by the n choose n/2, and this is also sharp because you can take the middle layer. And it seems that this result is earlier than the EKR theorem, and perhaps it's heavily related to the later world Orford problem, which is another field. Yeah. So one can also ask the same questions that if we require in the Spanner theorem, we require the one side difference is empty. It's not empty, and suppose the size of the one side difference belongs to some specific subset L. Then Frankl also showed the similar upper bound of this form. You can also get that this also comes from the linear algebraic method. And actually, there's a conjecture which remains open, that Frankl conjecture that this upper bound can be improved to n choose L. Yeah, that's how we start this project with Jingle one day, because one day he told me that he can solve this problem, and finally when we checked his argument that we can only solve we can verify this conjecture in some specific cases. Okay, and this is open. And another options is the symmetric difference. In 60 years ago, the Kleitman proved this very fundamental result, which state first the Kleitman is also very legendary. I mean, because at very beginning he majors in the physics, and he also got a PhD in physics and become a professor. And later, unfortunately, he met the Prodigy, and then he focused on the extremal combinatorics and made lots of the fundamental contribution in this field. And this result states that suppose in a set system, the pi-wise Hamming distance is bounded by some value d, then the set system can be upper bounded. When d is even and when d is odd, is slightly different form, but the extremal configuration is also very clean. For example, when d is even, you can take a Hamming ball of the radius k. So this result has lots of the application in coding theory, because the symmetric difference also sometimes is related to the Hamming distance. Yeah. Later we will also mention some more results on this Kleitman theorem. And several years ago, and Huang and Krugman and Porta, the above result is the proof is combinatorial, and later Huang and Krugman and Porta, they provide an algebraic proof of the Kleitman theorem, and also generalized this result. The restriction from the bounded symmetric difference to the symmetric difference belongs to some specific set. And I also, if I remember correctly, Zixiang and a visitor Ouyang Minhui, they also improved the upper bound related to this result in this summer. Okay, so let's turn to the main topic in today's talk. Today I want to introduce some tricks and basics in the linear algebraic method. So during the past 50 years, the linear algebra method has becomes more and more, important in the field of the combinatorics, and lots of the old conjecture was solved via some new techniques in linear algebra. And for example, at the very beginning, maybe 50 years ago, some mathematicians realized that one can use the linear algebraic method to study some geometric problem. For example, the S-distance set we will discuss later. And for example, a second statement is a purely combinatorial statement, which states that every 4 regular graphs plus an edge must contain 3 regular subgraphs, which can be proved via the combinatorial non-stereoms. But I think, for example, the second statement, there is no purely combinatorial proof. Yeah. So I also remember last year I proposed a problem how to give a combinatorial proof to the so-called Graham-Pollock theorem, which states that every complete graph cannot be decomposed into fewer than n-1 many complete bipartite graphs, which is also proved using the linear algebraic technique. But there is no purely combinatorial proof, like the second statement. Okay, and some recent advertisement of the perhaps lots of people know. For example, the finite field version of the Kakia set problem, because the original Kakia set problem is very important in the field of the analyze. And lots of people believe that the finite field version is as difficult as the original version, but the use a very elegant polynomial method to completely solve this problem. And this also inspired later the Erdős distinct distance problem, the solution of this long-standing problem. And for example, the 6th and the 7th statement for the cap set problem, some mathematicians use later the turnstile summary it as the slice rank method, which generalized the normal tensor rank of the matrix. And the last story, maybe most of us know, that the Professor Huang Hao, he used a very clean spectral argument to prove the non-standard sensitivity conjecture. Okay, so yeah. Okay. So today, this is said from Turnstile in some block. It said that the strategy of the linear algebraic method, mainly you can just associate some combinatorial objects or geometric objects into the zero set of some algebraic objects. For example, the polynomials with bounded degree, and then because we already know lots of about these algebraic objects, then you can tend back and inversely to control the original set of the combinatorial objects. Okay. So basically, when we apply the multilinear polynomial method, there are three. It consists of 3 steps. So first, you should associate the combinatorial objects or geometric objects with a sequence of polynomials. So actually, in my experience, once you realize that some problem can be proved use the polynomial method, you almost succeed, I think. So, yeah. So the second step is you should prove that the designed sequence of polynomials are linearly independent. It sometimes requires some algebraic argument, and finally you need to estimate the size of the space spanned by all possible such polynomials, which will give you some upper bound. Yeah. So actually, I think the main step is the first step, because once you realize it, then later you just spend time to. Okay, so usually how to prove the linear independence? So basically, it suffers to show that the above equations has only the trivial solution. This is by definition, and you can select the arbitrary field. For example, suppose you can prove the linear independence in the smaller fields, then it also works for the larger field. But sometimes working in the smaller field is easy to argue. I remember that 2 years ago, Jun Gao present a very beautiful work on a conjecture of Galais, which states that for a k-critical graph, the number of the cliques of size k-1 is at most some number. He proved the linearly independence in the F2 in the binary space. And okay, so usually we just evaluate or assign the same number. For example, we assign the k numbers of the variables, and you will obtain a coefficient matrix, and it suffers to show that the coefficient matrix is not it suffers to show that the coefficient matrix is not singular. Okay. So there are some simple proposition. actually the first proposition states that suppose the coefficient matrix is diagonal, then it of course it's linearly independent. And the second one states that suppose the coefficient matrix is lower triangular with non-zero diagonal entries, that's also linearly independent. But both of them are just some simple proposition. Suppose you have a deep understanding on the linear algebra, then there are also various ways to show that the polynomials are linearly independent. Yeah, beyond these two propositions. Okay, this is just some simple and quick ways. Okay. So basically, you can use just from the definition to list the coefficient matrix. Okay. So let me show you an example. So suppose we say a set, a d-dimensional Euclidean space, a subset in a d-dimensional Euclidean space is two distant sets. Suppose this set only determines at most two distinct Euclidean distances. So then what can we say about the maximum size of this subset? So by a simple construction, you can say, suppose we just choose some very small space in then we can check that if we write them in the form of using the vectors, then you can see the distance is either square root of 2 or 2. Right, this distance 2 and or distance square root of 2. And actually this construction is not optimal, because actually you can prove that the d plus 1 is also belong to this space. Right? So the currently best known lower bound is the d plus 1 choose 2. Yeah, not the d choose 2. Because you can prove this one. Okay. So what about the upper bound? So let's try the 3 steps I just listed. So first we to upper bound the size of the two distant set, we first associated with a sequence of polynomials. So for each point in A, we design the polynomial in this form. Suppose the distances are the square root of C1 and square root of C2. Okay. So the second step is very easy to prove is they are linearly independent, because if suppose assign the AI, then because the distance of AI and itself is 0, so the function is, so the value is C1, C2. And suppose you evaluate the other points, then the distance either square root of C1 or square root of C2, then the value must be 0. So it satisfies that means the coefficient matrix is the diagonal, then they are linearly independent. And so also we can check that the number of such polynomials, because the degree is at most 4. So trivially we can obtain the upper bound is the d to the 4. Yeah. So suppose you use the star and the bars trick, then you can see such a you can improve the d to the 4 to the d plus 4 choose 4. Okay. But actually, suppose you further expand this polynomial, then you can see that such polynomial must be a linear combination of the following monomials. There are possibly the 5 forms. The first forms only contribute to 1, and you can carefully count the possible forms, possible such monomials. Then you will obtain upper bound in the following form. The d plus 2 choose 2, and so and d plus 2, choose 2. And this is the first trick people will usually use. That means we can sometimes we can more carefully to estimate the space. The size of the space. Okay. And sometimes when we only consider the binary space, then we can remove all of the exponent, because the x to 1, because 0 to any is 0, and 1 to plus 1. Yeah, in the binary space we can use this trick. Okay. So today we will mainly discuss about the second trick. So based on some natural association, like the previous one, we associated one polynomial to one point. Then sometimes we can add more extra polynomials and extra set systems. Suppose we can prove that the union of the previous polynomials and the new extra polynomials are also linearly independent, but which will not increase the size of the space. Then we can gain some improvement. This is a very, very useful trick. For example, in this case, we can add d plus 1 more polynomials. And the form is very simple. The g0 is the constant 1. And the gix just the xi. And once you prove that those polynomials are linearly independent, then you can see the upper bound can be improved to d plus 2, choose 2. Yeah, because you added d plus 1 extra polynomials, and it does not increase the size of the whole space. This was first discovered by the Borkus. And later the Banai and Stanton generalized his idea to the NAS distance set. Yeah. One thing I was I'm curious that there are maybe more than 3 different proofs of this final result, and all of them use different algebraic techniques, but no purely combinatorial proof. Yeah, for this result, and this is the current best known upper bound. Yeah. There are still some gap. The d plus 2 choose 2. So I want to discuss more about the second trick. Let's recall the Frankl-Wilson theorem. The Frankl-Wilson theorem states that suppose the size of intersection of any pair of sets in the set system it belongs to the L, then the size can be upper bounded in this form. So simply we can define such polynomial, and it's quite easy to show they are linearly independent, and then we can obtain the such upper bound. Yeah, so this is simple. But later Snively improved the n choose I to from the n choose I to the n minus 1 choose I. So you look this improvement looks very simple, but actually, if I remember correctly, the Snively totally wrote 4 papers on this problem, and he using maybe 10 years. At the very beginning, he proved that suppose L is the 1, 2, 3, 4 to S is correct, and later then he can prove the set the L consists of consecutive sequence of integers is correct, and finally in 2003 he completely proved this theorem. And one main barrier is that it's very challenging to prove that the extra polynomials and the original polynomials are linearly independent. He associated the very natural set system, add them as extra polynomials, and finally he successfully proved that those polynomials and the previous one are linearly independent, and make this improvement. Yeah, using 10 years. So let's summarize. So about second trick, usually we will choose some appropriate extra polynomials and show the extra polynomials and the original polynomials are linearly independent. And in many previous work involve this trick. Actually, we can see all of this previous work involve this trick. The extra polynomials usually is very clean in nature. For example, which associate some explicit families. For example, such clean set system. But yeah, as I said, to prove they are linearly independent is very difficult. Sometimes you need the heavy understanding on the linear algebra. Yeah. So basically we focus on another direction. Some people like myself, we don't have the heavy linear algebra acknowledgement. So we only know some simple proposition like the diagonal or the lower triangular. But yeah, what we did is we can very carefully choose some families, and which satisfy some specific properties, and which will help us to prove the linearly independent very easily. Yeah. Then, at the cost, then we know little about the extra family we insert. Yeah. That means compared to the previous trick, is to show the linearly independent. It's not easy, but our method is easy. Then sometimes one in the previous method, suppose you prove the linearly independence, then you are done, because you already gained the improvement. You already know how you. Yeah. And but in our model, we do not know the what we do not completely know the structure of the extra family. So then our goal is to dig out further about the extra family. Yeah. Usually we need to combine some the structure analysis. So in some sense we can use the linear algebra method more flexible. So let me show you a simple example. Okay, so the theorem is the famous Katona shadow intersecting theorem, which states that for a k plus 1 uniform intersecting family, the size of the set system is at most the size of its k shadow. We can design three sequences of polynomials. In the blue board. So usually I like to write it this way. So here we write the polynomial, which is f and g, and sorry, FPI. Sorry. Okay, this is FPI. And we can evaluate the indicator vectors of the sets here. Then for the first part, we can see because it's k plus one uniform and intersecting. So we can see in this part, suppose we in this part there must be a diagonal matrix, because suppose the Fi and so suppose for distinct Fi and Fj, their intersection must belong to, the size of their intersection must belong to 1 to k. So the value must be 0. Okay. And because it's k plus 1 uniform, so suppose we assign the variable to the second polynomials, it must be 0. And for the third polynomials, it's the indicator polynomials, but because it's non-shadow, so it's also 0. Yeah. And we do not care about those parts, because we just to prove it's a lower triangular. And for the set system S, because we order them in some increasing order, so it must be triangular. It must be the lower triangular. So yeah, so it's 0. And because it's the size of the second, the size of each set in the second family is at most k minus 1. So suppose you assign here, this is the k uniform. So this must be 0. And this is diagonal. Okay, then we are done. We prove the linear independence. So the interesting thing is that what we insert is the non-shadow. Yeah, what we insert is the non-shadow, and we do not know any information about the non-shadow, right? So here we do not know any information about the non-shadow. However, to prove this statement, we can see each polynomial is degree n variables and of degree at most k. So the total size of the space is the entries I summation of the entries I from the 0 to k. And the size of F we just list here. And the size of the second family. The size of the second family is the summation of entries I from I equals 0 to k minus 1. So the difference is m choose k minus the difference is the non-shadow. The size of the non-shadow is n choose k minus the size of the shadow. So then we are done. Yeah. So in this case, we completely do not know anything about the non-shadow, but we can prove this statement. So in some so in our framework that sometimes we as I previously mentioned that we need to dig out the information about the extra families, but in this case we can completely ignore it. Yeah. Okay. So let's recall the Kleitman theorem. So the Kleitman theorem mainly states that suppose the pairwise symmetric difference is bounded by D, then the size is bounded by the Hamming-Borel size of the radius k. And in roughly 10 years ago, the Frankl proved a stability version of the Kleitman theorem, which states that suppose the family is not contained in any translation of the extremal configuration, then the size is significantly smaller than the previous upper bound. It's a Frankl's version of the stability result. Yeah, like the stability result of EKR theorem. The Hilton-Muller theorem states that suppose the structure is not a star, then the size is significantly smaller than n minus 1 choose k minus 1. Okay. So this result, the proof of this result is purely combinatorial, and also it takes advantage of another stability result of the Cartonar theorem, of the also proved by the Frankl. Yeah. So 2 years ago we proved a similar version, and with a slightly different quantitative bound. Yeah, this is almost the it's very similar. Yeah, and recently we have heard that some scholars they also proved some higher level of the stability result of Kleitman theorem, but I did not list here. They prove that suppose the family is also not a contained in a configuration of the extremal configuration of the Frankl's stability result, then it will be smaller, like, yeah. Okay, so how we prove this? We just use the linear algebra method. So first we do some operation, like we translate the all of the sets to guarantee that the empty set contains in the family and some extra properties. And the main step is that we associated these polynomials with the set. So you can easily see that. So those part is the correct form to represent the symmetric difference. Yeah, I just find the correct way to represent the symmetric difference. So later we just so those parts you can easily to prove they are linearly independent, and then we also insert the non-shadow, and it's not hard to prove they are linearly independent. Then we can obtain this form, and later we just need to analyze the size of the shadow, size of the non-shadow. Suppose the non-shadow is large, then we are done. Suppose the non-shadow is very large, we are done. So suppose the non-shadow is small, then the size of the non-shadow is small, then that means the size of the shadow is large. Then we can apply some structure analysis to show some to lead to some contradiction. Yeah. So this is a sketch of the proof. So I think our proof consists only one page. Yeah, because the structure analysis is also very simple. Okay. So we can also apply this. We can also change the condition from the bounded symmetric difference to bounded one-side, set-wise difference, and obtain a similar stability result. This can answer the Frankl's conjecture in some specific cases. Yeah. Okay. So let me, yeah, time permits. Let me mention some of recent work using the multilinear polynomial method. So I think there are lots of the proofs, perhaps more than 10 different proofs about the EKR theorem. And some of them involve the linear algebra method. For example, there are at least 2 proofs using the spectral theory. One, for example, you can relate it to the independence number of the Kneser graph, and using the because we know almost all of the spectrum, the information of the spectrum of the Kneser graph, so we can use the integral bound. And another way is because you know the largest eigenvalue and the smallest eigenvalue, so you can also use found like, so I forgot the correct form about the largest eigenvalue and the smallest eigenvalue. So did you know about the proof of EKR theorem use multilinear polynomial method? Perhaps it's not very common. So here you can partition the, sorry, this is not partition F to the F0 and F1. So totally you can consider these 4 families and associated each with a sequence of polynomials. And yeah, sorry, I did not write the form of the polynomials. You can imagine it. Yeah. So then once you prove they are linearly independent, then you can prove the EKR theorem in this way. Yeah. I think it's not common. Okay. So here we can pick a member P arbitrarily, as its fixed point, fixed element. So during past 2 years, I sometimes I thought how to prove the algebraic proof to the Hilton-Muller theorem. The Hilton-Muller theorem states that suppose the K-uniform intersecting family is not a star, it's not trivially intersecting, then the size is significantly smaller than the size of the star. And later, maybe in 10 years ago, Hanjie and Koyakawa, and they proved that suppose you also forbid the extremal configurations in the Hilton-Muller theorem, then what can we say about the set system? They proved a further stability result of that means the stability result for the Hilton-Muller theorem, which I call the second level of the stability result. And actually later the Mubai and someone else, they proved the third level. And recently we can show arbitrary T's level of the stability result using the algebraic method. So our statement states reads like this, because I simplified the statement. I don't want to write a paper like using too many the structure analysis. So I have made some extra assumptions. The first assumption is the integer k, the k uniform. The uniformity is at least t plus 2. T means the level of the stability. Yeah. So another assumption is the natural condition is n is larger than 2k plus 1. So here is roughly n larger than 3.6k, like. Okay. So we prove that suppose the set system, if you forbidden, if the set system is not contained in the extremal configurations at any T0 levels of stability result, and T0 is smaller than T, then the size can be. And interestingly, this upper bound is sharp, because in each level you can find extremal configurations. Yeah. Yeah, but for the clean proof, I made 2 assumptions. The first is k, and another is n. Okay. So, at very beginning, I came up with how to use the multilinear polynomial. I can insert this subset of non-shadow. But during a long time, I do not know how to combine the the old information. I mean, how to mix the old information of these 5 families to obtain the correct statement of the stability result. But several months ago, my academic brother he told me that we can ignore the F0. We can only use this 4-set system. We do not use all of the 5-state set system. We can remove the F0, and then we can discuss the size of the F0. And then I realized that it works so very smooth. Okay. So once we obtain this, I think people can also obtain this using the combinatorial argument, avoiding the linear algebraic method. Yeah. Okay, and the remaining, to obtain the stability result, the remaining is just to analyze the size of the the partial non-shadow and the F0. Yeah. It involves lots of the structure analysis. Okay, so finally, I plan to introduce some very recent work. So the result, the problem is like this. I think most of us know the definition of the VC dimension. So one of the fundamental results in the theorem of VC dimension is Chalet lemma, which states that suppose a CL system has VC dimension at most D, then the size can be upper bounded by the summation of the V choose size of V choose I, the I from 0 to D. And this is sharp because you can take a Hamming ball of size of radius D over 2. Right. Oh, sorry, Hamming ball of size of radius D. Yeah, sorry. And yeah, so this is a very fundamental result. And it's a non-uniform version. Yeah, we do not require that the set system is each set has a size k or something. But do you know how to prove this using linear algebra method? Suppose it's also not very common because most of the proofs just using the induction and some shift operation and use induction. Let me remember. Yeah, I think the proof the sketch like this. First, you can show that all of the indicate polynomials are linearly independent. Right, just all of these are linearly independent, right? So what we need to do is to control the size of the all possible polynomials. So actually, for each monomial of the degree at least d plus 1, for each such monomial, you can represent it as by the condition of VC dimension. You can represent such monomial into a polynomial of degree at most d. Then you are done. Yeah.
So here D is the VC dimension?
Yeah, D is VC dimension. I mean, well, first we need to show that any polynomials are linearly independent because indicator polynomials must be linearly independent. Then for each monomial of degree at least d plus 1, you can represent it to some linear combinations of the polynomials of monomials of degree at most d using the condition of VC dimension. Yeah. Okay. So based on
assuming the values are 0 and 0, 1 or something, you may need something, right?
Yeah, yeah. You know, because for each set of d plus 1, it cannot be a shattered set. So for each size set of the size d plus 1, there must exist some set such that is not this for any So you can, based on this B, to design a polynomial and to represent it to the low degree polynomial. So, but the non-uniform case is simple and people will understand, but the uniform case is surprisingly open. So the question is, the simplest question is, what is the maximum size of a k-uniform set system with the VC dimension is less than k? So maybe in 40 years ago, the people first studied this problem because they found that the star, the k-uniform star, has the VC dimension exactly k minus 1. So they conjecture that, so of course the n minus 1 choose k minus 1 is a natural lower bound for this problem. So they conjecture that this should be the sharp upper bound, a sharp lower bound, which greatly they generalize the EKR theorem in this form. And Frankl and Janusz-Peg, they also proved a very clean upper bound. The upper bound is n choose k minus 1. So let me list here. The lower bound is n minus 1 choose k minus 1, and the upper bound is n minus 1 choose k. So both sides is very clean. So usually in the field of the extremal set theory, the answer is either this or this, right? Usually, because people don't like the ugly solution. Yeah.
It's the n choose k minus 1 is what we have on
Oh, n choose 1.
N choose k minus 1 or n minus 1 choose k for
Oh, I'm sorry. Oh, sorry. N. Yeah, thank you.
So is there a reason that they have the conjecture only when n is large? Is there some obvious contract there?
I don't know. Sorry. And you can see that suppose n is smaller than 2k minus 1, then the upper bound is sharp because they are the same, right? Sorry, suppose the n equals 2k minus 1, they are the same, right? They are the same. Okay. So. Okay, so very surprisingly, there are two unexpected results. The first is that the lower bound is not sharp. They construct a set system which has size n minus 1 choose k minus 1 plus something. N minus 4 choose k minus 3. And actually, there are infinitely many isomorphic non-isomorphic configurations attend this lower bound. So lots of people believe that this lower bound is sharp. Yeah, this lower bound is sharp. On the other hand, Mubai and Professor Zhao Yi, they very cleverly combine some algebraic technicals and the sunflower lemma to show that the upper bound is also not tight. But it only works when k minus 1 is a prime power. Yeah. And recently we try to improve because they remarked that in their paper they remarked that their method only works for the one k minus 1 is a prime power, and they show some counterexample or some proposition to show that suppose k minus 1 is not a prime power, then their method does not work. Okay. So we first try to find a multilinear polynomial method of the Frankl pack above. So because the set system is K uniform, so we associated each set in this family F. We assign a polynomial because due to the definition of the VC dimension, for each D plus 1 set, for each K set, there must exist some subset. Is not shattered. So let me see. For each Fi, there must exist some Bi, such that let me write. For each Fi, there must exist some Bi, such that so this is from the definition of the VC dimension. And we can define a polynomial in this way. To guarantee that such polynomial has degree at most k, so we need to at most k minus 1, we need to minus some monomial of degree exactly k. Yeah. So you can check that those polynomials are linear independent. And secondly, we can insert the O sets of size at most k minus 2 using the polynomial minus k, and times is indicates this is second sequence, and the final sequence is a non-shadow. Non-shadow, right? This, and we just use this indicate polynomial, and we can use a similar way to check that those polynomials are linearly independent, and which gives that the size of the set system is at most is k minus 1 shadow. And coincidentally, we find that this also generalizes the Katuna intersection theorem because it's intersecting family. The VC dimension is at most k minus 1, right? So it's a generalization. And later we find that the upbound is not sharp. Actually, we can add more extra polynomial. We came from the extra family from the extra family from the from this, and we use some combinatorial argument to show that such set must exist, and we associated with correct polynomials and proved linearly independent. Yeah. But we only minus 1, they are bound. But actually, I think refine our argument can minus some large number, but it's not polynomially in it. It's not easy. Yeah. So.
Also, you mean this less you just prove F is
minus 1. Minus 1. Yeah. Yeah. But if you try to use more combinatorial argument to I guess our method cannot minus some polynomial in it. Maybe log in is easy, but yeah. But the gap is the polynomial in it, from the lower bound and the upper bound, between the lower bound and upper bound. Okay, thank you. All right.
Thank you. Any questions?
Do you know whether there's any systematic way to go the other direction? So if you have a polynomial proof for some theorem, to find a non-proof. I know that there's still some theorems for which no one knows, but are there some conditions under which we can do this?
I don't know. For example, some fundamental statement like the Kleitman theorem. Previously, it only has the combinatorial proof, but several years ago, Frankl they proved they gave some algebraic proof. Then, for example, the EKR, for example, the stability result of EKR. I suspect lots of the results you can carefully to select the polynomials to give the algebraic proof.
Right, but
inversely, yes, it's not easy. For example, I think all of the results in the first page, all of such nice results, I don't find the purely combinatorial proof. Yeah.
But are there maybe some easier results where this translation was successful?
Yeah. For example, the EKI is so.
Right, but there we had the combinatorial proof first, right?
Oh,
like what I.
You mean historical speaking?
Yeah,
but it's hard to say.
Because often, I mean, for many of these things, it would help a lot if we would have a combinatorial proof.
Yeah, right.
Because they seem to be more adaptive.
Yeah. For example, for the cap set in the finite field, I think no one has the combinatorial proof to exponentially improve this. Yeah. But our framework just try to use the polynomial more flexibly to combine some the algebraic and the combinatorial argument together to mix the.
So your theorems can also, your proof method also gives you some modular version, right? So for some modular P.
Oh yeah. Sometimes if you put the if you want to show the linear independence in the finite field, sometimes it's perhaps easier, but in lots of the results, for example, the L intersecting family, there are lots of the P modular version or Q modular version. Yeah. Some Q analog.
Any other questions? So let's take